All right, let's do it. How's everybody doing? Everybody awake? Ready? Excited? All of the above? Hopefully. So today it's going to be a relatively short day. And in fact, it might be the last day of lecture for Python for STEM. So at least for this year. After today, we're going to have Ted coming back. Professor Ted Rogers is going to come back and tell us about infectious disease models and how to solve them numerically. This is, of course, very timely. This is inspired by the pandemic, and so you're going to be able to make little curves like this, which track the numbers of infected people. And you're going to understand where those models come from. And he might lecture about other stuff, but we'll see. So he's going to pick things up on Friday of this week. So yeah, so this is going to be the last day for me. And so I figured first, let's start as always. Why don't you tell me how you're doing? Put in the chat in the Q&A, how you feeling? Where, how are things on your corner of the world? I always like to read and hear about you. So it's nice. So please do that. Also, if you are interested in continuing to learn, from me and my colleagues, despite the fact that I won't be lecturing here, I am in collaboration with my collaborator, Andrew Jakora. We are hosting some mentoring lectures for our mentees on nuclear physics, and we've made those publicly available in the YouTube page of REYES, so you can see them there. So you're still going to be able to hear me and others talk about nuclear physics, so I won't be going too far. Greg, do you want to read some of the comments?
I do, actually. One of them sounds really exciting, so we'll get to that one then. But Sid says, doing awesome. I hope you're doing amazing too.
Maybe not as good as you said, but I'm doing all right. I like that. Yeah, awesome.
The one I'm most excited about reading here is Adriana says that they're doing well, but they worked on their telescope this morning. So that was fun.
Wow. Well, you're doing well despite the fact that you're working on your telescope, or you're doing well because you were working on your telescope? Maybe you should clarify. And what kind of telescope? We want details.
Additionally, Austin says that they're doing well and they're feeling very excited about the mentorship program.
Awesome. I'm glad, Austin. Thanks for participating.
And additionally, Anonymous says they're doing good and they wonder how Jazzy is.
Oh, Jazzy. She's okay. She's very old. She's 17. And so she's good. She's at home resting. In fact, my neighbor was about to take her for a walk because she's very old. And so she needs to go out. I mean, walk is maybe a generous verb. She just goes out there and sits by the grass. So she's living her good life though.
And we have some clarification from Adriana that say they're doing well because of the telescope and that the telescope is an 8-inch Newtonian refractor.
Ah, okay. Huh? I'm impressed.
We just got one more. Drea says they're doing great and they just heard about this course an hour ago, so they're tuning in for the first time.
Oh, wow. Okay. Very good. So welcome to the course. So this, let me back up a little bit to give you a little bit of context, because this is week 6 of this lecture series. You don't need to necessarily start from the beginning, but I would encourage you to start from the beginning. Some of the things that I will use here involve especially content that was covered in the previous lecture, which was Friday. And so if you're new to the course, let me plug our YouTube page where you can see everything, all the videos that were, all of our classes have been recorded and posted on YouTube page. So the easiest way to go to the YouTube page is go to odu.edu/regis, okay? And if you go to the bottom, there's a little symbol here for YouTube. You click it, it's going to go to YouTube, and you see, here I am. Actually, we're live in YouTube, so I could hit that, and then there's going to be an infinite number of mirrors, right? We don't want to do that. But if you go to the bottom, you'll see all the recent uploads, and so you'll be able to find all the Python for STEM videos. Okay, so soon enough, we'll start making. In fact, we taught this class last year, and we had a little playlist for Python for physics. We called it Python for physics last year. We're going to make one playlist for Python for STEM, so we'll make your work, your life even easier. But I would recommend go to the beginning and just go do the full ride from beginning to end. Okay, but you can stick around to this lecture. You'll learn something. Some of it may be over your head, but some of it may not. So feel free to stick around.
In the time of that, we've actually got a few more people asking both questions and checking in.
Okay.
Philip says that the program's been great so far, and they're looking forward to see what the mentorship program holds. Cheyenne says that there's an upcoming office hour meeting for the mentorship program this week. When is it?
Yeah, so we were gonna do, so for those of you that are new and perhaps hearing about this mentorship program for the first time, I just deleted this page. Jeez, so sloppy. So we created a mentor program for students that want to learn about different sciences. I am hosting one of these mentor opportunities, and I decided to make it available to everybody that wanted to join. And so we have, I don't know, somewhere around 150 participants. And so we're recording our sessions and posting them here. And so in fact, if you go to the YouTube page, you can check out our latest video. And we are also going to be hosting some meetings, which are not going to be casted live, for the mentees. There's going to be some office hours. There was a logistical issue. I'm not sure. I was planning to host them this Thursday. I don't know if we're going to be able to host it this Thursday. We'll be sending you emails about this. Okay, so don't worry. We'll send you information on how to log in and when it will be. It's probably going to be the following Thursday. Okay. My meetings, the nuclear physics ones, if you're going to learn about nuclear physics, they're every Monday. They're going to be posted here, and so you're welcome to check it out. Go.
And we have one final person to mention. I think we can go through before we get started. Emiliano Reina asks, have you already sent the link for being a panelist? They already sent the signed papers. I don't know if that's something that address sooner rather than later.
Yeah, so we're working on it. So if you send your paperwork, appreciate it, then we have it. I'm just bombarded with emails and we're slowly sifting through them. So just be patient. We managed to get most of you to be panelists yesterday. Hopefully we'll be able to get the rest. Also, let me remind everybody that while I have the YouTube page here, that you should be watching all the content of all the videos that have been hosted, because we're going to have a trivia night soon enough, and if you want to participate, that's only fun if you know trivia that was presented at Regis. And so in your free time, go through all those endless hours of material. You'll be learning a lot of content from different sciences. And last, we are also hosting a video competition where we asked you to send videos, short little videos, explaining some concepts that were taught in any of our classes, in any of our lecture series. So if you haven't started working on that, consider doing it. as you can see, being able to articulate things creatively and clearly is a very useful tool that will have immense effects in your career path, regardless of what they would be. So I can't recommend that strongly enough. All right. Okay. Enough chit-chatting. Let's get to science. Let's get to some math. So we left off last week. Yeah, Friday, talking about first order differential equations. I covered it, so I figured I would cover it again, just to remind you and see if there's any questions. Because guess what? What are we going to do next? Second order, right? What comes after first, second? So it makes sense. All right, so first order differential equations, right? I started by mentioning, and to the newbie, if you're not familiar with calculus, that's okay. The previous video, I introduced all the calculus concepts that you needed for this exercises. So you don't need to know calculus in this class. We teach you everything you need to know. All right. So here's an example of differential equation where typically you have some function f that you don't know and some function g that you do know, and you're trying to solve for f. And so you have a differential equation, and you got to figure out how to deduce what the function is f given knowing its derivative. And I motivated this by saying that most equations in physics and consequently in nature are either differential equations or integral equations. And so the simplest case that we can consider is a case like this, where you have exactly what I just said. You have a derivative of some unknown function f, and you know a function g. The derivative is nothing more than the difference of f divided by the difference in the independent variable x, which we've denoted the difference, the separation between points we define by a. Ultimately, we have to take this limit where a goes to 0, and that defines the derivative, right? That's the definition of a derivative. It's this limit where a goes to 0. That is conceptually hard to evaluate, but numerically it's very easy if we don't take explicitly the limit where a goes to 0, and instead we just evaluate a at increasingly small numbers and then check that our result converges to some desired value. And so if I don't take the limit where a goes to 0, then this function, the derivative, the finite difference, the derivative gets replaced by a finite difference. And what I'm evaluating is f evaluated at x plus a minus f evaluated at x minus a, all divided by the difference between this point and this point, which you see the difference is 2a. Okay. And so this now amounts to an algebraic equation. I'm skipping a little bit. I'm going kind of fast. Last time I broke it down a little bit because it's just a review, right? It's just a reminder. Then once I have this, then I can multiply both sides by 2a, and then add to both sides f evaluated at x minus a, and I get this equation. Okay. All right. Everybody's with me? Are there any questions, comments?
There's a quick question. I'm not sure if it's corresponding to Friday's lecture or not, but Philip asks, was the method used to solve the differential equation the Euler method?
It was, yep.
Okay, you did cover that on Friday?
No, I just didn't call it, but it is the Euler method.
Okay.
I've been shying away. I know that some of you are more advanced, but I shy away from using any terminology. I want people to not rely on nomenclature and names, and instead rely on their intuition. And I think sometimes, I don't know, I struggle remembering the different names, which were a lot of time follow the name of the person that first proposed it, right? It's kind of arbitrary. It doesn't really tell you anything meaningful about the mechanics of what's happening, right? I prefer to just develop an intuition and just remove all the terminology to a side. That's just my flavor, but yeah, it is the Euler method. And so then once you have this equation, right, this equation on the bottom, then what we can do is just solve it iteratively, right? And I explain exactly how to do this. You can just, so I proceeded first to make a variable transformation where I define x to be x naught plus a, and so I had this equation, and then I said, x naught is just some variable. It doesn't really mean anything, so I could call it x, right? It doesn't mean anything until I put a number into it, right? So if I'm calling it x naught, why not call it x? That's the idea. And so then this equation is exactly the same equation as this one, okay? And then the point is that this equation already is everything I need to do to be able to solve the differential equation. Sorry. This gives me a solution to a differential equation, assuming first that I know the derivative, g, right? And that I know an initial value for f. And so if you give me some initial value of f, say at some point x equals 0, then the next point, which corresponds to x equals 2a, is determined from the value at f at x equals 0. Okay, it's just equal to this. And then the next one, well, the next one is just going to be the previous one plus the value of g at 3a times 2a, etc., etc. I just keep applying this equation over here. All right, so that's the basic idea. And then in practice, the way that you implement this numerically is by doing a for loop. And here I wrote a piece of code, which I think was the last piece of code I showed, where I define a function diff underscore eq, which depends on some unknown function g, some input value f naught, and then the axis over which I'm integrating, or sorry, over which I'm I want to determine the function, sorry. And then a is the steps, right? It tells me the steps between the different points. Here, there's a lot of comments, right? Remember, the syntax for comments is I can use one of the ways that you can make large text that is commented out is using 3 quotation marks, and then you close it with 3 quotation marks. And so I decided to make my output a list, which is going to be the same length as the x. And so then I loop over all the possible instances, that all the possible indices of the x. For each one, I grab the previous element of my output list, which is fs. This -1 is the previous element. Then I add this shift. So I grab the previous one and I add the shift, and the shift is equal to g evaluated. You have to be careful here with the indices, right? And so here I'm grabbing it at the next step at x. So I subtract 1 instead, subtract a instead of adding 1. I explain this over here, and then I multiply it by 2a, and then this is df, right? So then all I have to add to fs is add f plus df. All right, this is a little compact, and so this is a great place to stop and see if people have questions. We covered this last time, but maybe you didn't quite, maybe some things that you didn't appreciate the previous time, maybe you appreciate it now, maybe some questions arise. So are there any questions about this?
I think we should wait a second to see if any questions come in, but I think it's important to reiterate that this is something that it takes a few times of seeing before it really sinks in how this stuff works. So
yeah, I agree. And to the newbie, don't get scared. This is the ones that if you're here for the first time, like I said, this is something I covered last time and I went a lot slower. And so if it doesn't make sense now, then you know, I would encourage you to go check out the previous video and hopefully it'll make sense the second time you see it. Do you have a comment or questions?
Yeah, we have one comment corresponding to this. I think I'll start with that. Philip asks, which x's are being plotted in the previous slide?
So x here is 0, right? Oh, yeah. So you see, so here, so x, so in this case, f, so this is my starting point, right? This one is clear. So my starting point is at x equals 0. The next point is at x equals 2a, right? And so then here that would correspond to this variable being 0, right? Because this whole thing is this variable over here. And so that means that this variable has to be 0, which means that this one has to be 0. And so the next point is at f0 plus ga over 2a. Yeah. So the point is that I have this equation, it can be confusing. I think a lot of times we struggle to think about variables as things that we can just relabel any which way, right? So I've called this x naught previously, and then I say, it doesn't matter, I can just call this x, right? And I can, right? But I can also call this whole thing x, right? So this would be x minus 2a, right? And this would be x minus a, right? I can call it whatever, right? It's just a placeholder. And so the point is that when I have it on the figure, I have this at 0, then at 2a, then at 4a, 6a, right? And this has to be in steps of 2a's, right? Because I have this shift, right here. But the point is that when this is equal to, I know the value, I need to know this value. I need to know the value of f at x equals 0, right? But when x is equal to 2a, right? This means that this is equal to 0, right? Which means that this is equal to a, right? And that's exactly what I have here. I have that this is equal to f at 0 plus g at a times 2a. Right? And when this is not equal to 2a, but instead is equal to 4a, so the next point, right, is going to be 4a. The next one's going to be 4a minus 2a, right? So that's equal to 2a. The next one is going to be 4a minus a, which is also known as 3a, right? So that's going to be this point right here. Which, let me clean up this because I'm not going to keep going. So then this is going to be, well, the previous point, which was 2a, right? Plus g at 3a plus times 2a. Does that make sense?
I think you covered it. They said thank you, but they also said it just wasn't clear to them which was the independent variable. So,
gotcha. All right.
Additionally, before we continue, there's a general question from Adriana talking about the previous coding assignment you had assigned, whether or not they should put their code in Slack. So I'd just like to say, yeah, I'm actually on Slack right now. And so if you post it in the help channel, I'd be happy to look through it while he continues lecturing.
Okay. All right, so that's a little code for solving differential equations. And then I suggested you put this to a test using simple examples. And the reason why these are simple is because we know the solutions to them. Remember, if you have seen calculus, if you have seen calculus, you know that the derivative of an exponential, which exponential am I considering? The derivative of e to the x with respect to x, which is equal to e to the x, right? Which other ones? I think we did sine, right? The derivative of negative cosine with respect to x. Well, this is equal to negative the derivative of cosine, which is equal to negative sine x, which is equal to sine of x. And then the other one was the derivative. So the point is that we're solving for this, right? We're solving, this is our unknown in the first case. This is our unknown in the second case. The third case, we did the derivative of sine is equal to cosine of x. Okay. And so in the third case, this is our unknown that we're solving for numerically. Sorry. So the point is that although these are in principle unknowns, there are known unknowns, right? We know this is what we're looking for. Let's fill it up. This is the thing we're looking for. No, trying to make a little pretty box. There we go. Oh my God, it's like a weird rhombus. All right, that was a little better. Oh, all right. Parallelograms is what you guys get. So those are the things that we don't know, but we know the solutions because we know a little bit of calculus. If you don't know calculus, that's okay. I'm telling you the solution. And so we're looking for the things on the box, right? Which is what our algorithm gives us. A little piece of code over here, right? That's going to give us a function. And so let's test it out. In the first case, the derivative is an exponential. And we know that if the derivative is an exponential, then the solution has to be an exponential. We need to give it a value at x equals 0, right? And so we set this to 1. And look at this. My numerical solution is this, this red curve, and the green are the points that I expected from knowing the solution. On the bottom, I'm just valuing the derivative. The next one is sine is a derivative, right? But we know that if the derivative is sine, from a little bit of calculus, we know that the function has to be negative cosine. I picked the original point to be at x equals 0 to be -1. And so this is negative cosine right here. My numerical solution is red, and then the solution that was expected is in green. Here's a derivative. And then last case is the the derivative is cosine, right? The derivative is cosine over here. I pick my function to be 0 at x equals 0, and then red is my numerical solution, and then in green is what I expected to get. Pretty good. How about that? All right, is everybody happy with this? Have people been able to reproduce this yet? All right, maybe we'll keep going, and if people want to brag about their solutions or complain about not having gotten it, you're free. All right, we've mastered first order differential equations. There's nothing else I could teach you. So let's jump into second order differential equations because they're more interesting. In fact, they're not that much more interesting. They're easy. They're just maybe slightly harder, okay? They're not that much harder. So you've already learned that velocity is the derivative of position with respect to time, right? We talked about how velocities can be understood in terms of the slope of a curve, where we take the difference between 2 points to be infinitesimally small. And so the difference between the 2 points going to 0, that amounts to the tangent at that point. And mathematically, it just amounts to taking the limit where the change in position divided by the change in time, where the change in time is going to 0. Okay, this is the derivative. And this is velocity. And we know, and I covered acceleration, which is the derivative of velocity with respect to time, which again can just be defined exactly the same way, but now instead of the change in position here, I have the change in velocity, right? This capital delta just means change, while on the bottom I have the change in time. I'm taking the limit as the change in time goes to 0. This is a derivative of velocity with respect to time, but velocity itself is a derivative, and so the acceleration is the second derivative of the position with respect to time. It's just, it is what it is, right? All right, you're all with me. Good. So why did I refresh this? Well, in Professor Ted Rogers' class, you saw some equations which describe the kinematics of moving objects. And you had the position as a function of time, and it was this, you had these solutions where x as a function of time is equal to x0, which was the original position, plus v0 times t plus ax divided by 2 t squared. Same thing for y's. And you use this to describe the motion of projectiles that are moving, and you had to hit a monster, yada, 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 right? But the question is, where did these equations come from? And these equations, they're the solutions to the differential, the second order differential equations for position and time, for position in x and position in y, right? So you have two coordinates, and so you have second order differential equations, and the second derivatives are the acceleration in x and the acceleration in y. In fact, they're not the solutions of this, but in fact, they're the solutions when you assume that the accelerations are constant. This is important, and we'll test this. What we're going to do is we're going to be able to write code that is going to be able to solve these differential equations for any acceleration, and we'll test if they indeed reproduce these solutions when the accelerations are constant and or when they're not constant, basically. All right, so maybe it's a bit of a mouthful. So now let's take a step back. Let's do a little more general scenario, just like before. Although we have some kinematics in mind, we want to be able to solve differential equations for any systems. Okay, so here is the kind of equation that we want to solve. It's this second order differential equation. Again, in this case, so we have, no, I don't want to make boxes now. Thank you very much. Wait, yeah, okay, so now my independent variable, I'm calling it t because I'm thinking about time, but I could have called it whatever. It could have been x, right? I called it t to just keep you on your toes. All right, so in this case, this is known. Meanwhile, this is unknown. Okay. And so this looks like a daunting task to solve, right? But it's actually not that hard because remember, if we remember that this function that the function that we're trying to solve also has a single derivative. And so if we call that g of t, then we can rewrite this equation as replace this equation, a second order differential equation, with two first order differential equations. The first one is this one right here. This is my first differential, my first order differential equation. All right, which is again unknown, right? And this one is also unknown. Okay, except we're going to make a requirement. We're going to require that we do know f and g at the initial conditions. Okay, so now if I grab this equation and this equation together, I see the following. I see that I can rewrite that the one above as the derivative. So the second derivative is just applying the derivative twice. It's nothing more than that. So let me just rewrite it. Sorry, let me not skip steps. So the second derivative of f of t is equal to the derivative being applied twice. Okay. But this derivative, this thing right here, is equal to g of t from the first equation. So this is equal to the derivative of g of t, which from my original equation is equal to h of t. So this is in fact my second first order differential equation. And so I have two first order differential equations. Let me rewrite them. 1 and 2. The first one is the dt of f is equal to g of t, right? And then that the derivative of g is equal to h. And so I have two unknowns, which I can rewrite in terms of algebraic expressions. So I have two functions, two unknowns, right? Which is going to require two initial conditions. I'm going to require that I have g, so I need to know f at 0. I need to know G at 0. And of course, I need to know H everywhere. So if I know those two, I'm going to be able to solve these two equations simultaneously. That's my claim. Let me show you how. And the way that I do this, right, is doing the same exact steps that I did before. So let me copy this over here. Boop, boop, boop. Right. So for a finite difference, right, this amounts to f of t plus a minus a is not equal. Okay, first, I mean, let me just rewrite this. I can just rewrite it. This, remember, it's just nothing more than taking a to 0. This is the definition of the derivative. Right? Same thing for the bottom. This is equal to the limit as a goes to 0 of g of t plus a minus g of t minus a divided by 2a. Right? Nothing mysterious there, hopefully, right? And so then from the first equation, I get that f of t. Now, going from here to here, I'm going to say a does not go to 0. Okay. I'm just going to assume it's small enough, but it's not equal to 0. Then I just follow the same steps as before, right? Made a typo. Bada bing, bada boom. Same thing as before, right? And then 2, right, looks exactly the same, but with the f's replaced with g's, and then the g replaced with an h. Awesome. We're good. And then I can, I can call this t naught, right? And I can do the same variable transformation as before. I could do whatever I want, but it just gave me a relationship between points that are separated by 2a, right? Okay. So maybe let's just write it fully. After I've done the variable transformations, I just get exactly what is on the slide. Okay. Good. All right. So there's one subtlety here, and this is why I decided to do this. So you see the G's are being evaluated at t or t plus 2a, right? Oh, sorry, I'm covering this up. They're either evaluating at t and t plus 2a. Well, here, what we need is t at plus a. Sorry, at t plus a. So this is a t plus 2a. This is not any one of these points. And so what we can do is say, this is equal to approximately. We're going to approximate this with the average of the point right adjacent to it and the point right before it. So right after and right before it, and divided by 2a. In fact, you could have picked one or the other. You don't have to take the average. I took the average, but you could have picked the one above or one below, and you would have gotten the same answer. Assuming a is small. And so this right here is telling us the error that we're making. This big O here is a calligraphic O. And it's telling you the size of the error that you're making. So it's telling you how things will behave if you take a to 0, how quickly you will converge to that answer. So if a is a very small number, a squared is smaller than a, right? If a is less than 1, you have this condition. And so if you can show that your algorithm, behaves like a to some higher power, that's always better. It's always going to converge faster, right? So here I made some arguments as to why it has to be a squared. Are there any questions or comments?
We don't have any. Well, we just got one for this, but there was a quick question on the previous assignment that you just signed for what the objective was. Adriana asks if we are inputting a function and finding its integral in the previous assignment.
No, in the previous assignment, what you're trying to find is the solution to this differential equation. So I'm giving you cases where we know the answer, right? And so this is to test your code for solving differential equations. That's the objective, is to show that you're coding this correctly. And I'm giving you, so why do you want to make sure that your code is working correctly? Because then you want to eventually apply it to cases where you don't know the answer. And so you need to be able to have confidence by reproducing known results. So
okay, I think just to be, we haven't covered numerical integration, right?
We haven't covered numerical integration, no.
So then, corresponding to the stuff you just went over on second order differential equations, Austin says that they've seen the difference quotient written as f of x plus a minus f of x all divided by h. Would this alternative definition still work here?
Sorry, so f evaluated what?
So they've seen the difference quotient written as f of x plus a minus f of x all divided by h.
Yeah, so that will give you it. So that I see, not divided by h, but divided by a.
Yeah, yes, divided by a, yes.
So that will work. It's just it actually converges slower with a. So proving this requires you knowing a little bit of calculus, but you can show that will converge to the derivative. There's going to have order a errors, while what I'm proposing will have order a squared errors. For sufficiently small a's, you won't be able to see it. So this is to say, in these tests that we did, so in these tests that we did, where we calculated the derivatives with respect to a, you see how this is quadratic. Has a quadratic behaviors. If you were to do what you suggested, it would be linear. And so it would converge slower to the right answer. You're welcome to test it out though. So
They say thank you.
awesome. All right. So now that we know how to do this, right? This is just two first order differential equations. And so let's put these ideas to the test. So we know the solutions to the positions and velocities as a function of time. These were given by Ted in his class. Here they are. So the first thing that I ask you is to write code to evaluate both x and so the position as a function of time for a constant acceleration and velocity as a function of time for a constant acceleration. Okay. So what we're going to do, I'm not going to prove this, that these are the right solutions, but we're going to test them. Okay. We're going to write code for solving second order differential equations. The claim is that these are solutions to second order differential equations when the acceleration is constant. We're going to test that out. Okay. Meaning when, what I called, remember what I called h was my acceleration, right? So if h is independent of time, that's the scenario where we should be able to solve these, obtain these same solutions. So here's my little code for defining x as a function of time. In fact, it holds for both x and y because it's just a function which has some variables. So, the code doesn't know anything about what x naught, v naught, a naught means. That could be a placeholder for y naught, v naught, y, a y, right? All right, so here's my little code for x as a function of time. Here's my little code for velocity as a function of time. It's just a constant term plus a linear term in time. That's it. All right.
Before we get too far into this, someone has asked if maybe you could spend a little bit more time explaining what big O was for the error previously.
Yeah, so that's a good question. So the general idea is the following: is we obtain in general you have let's say I have a function. What do I call it? Let's call it L. And I've determined this numerically. And in some solution that let's say I'm trying to determine L and I'm using a finite A, right? And let's say I obtain it here, okay? For some value of A, and A is equal to 0 over here. This is 0 over here, there's some value A naught, right? And really what I want is A naught. So it has a value that I want, right? And so really what I want is L when A is 0, right? Ultimately, I want to be able to have a result that is insensitive to how I've used to discretize the separation between points in space, because that's what I'm doing. I'm essentially saying my objects can only live in certain times or in certain points, and I'm taking differences between those, right? But ultimately, I need to take the limit where those go to 0. But I can't do that in practice numerically. And so I'm fixed, I have this finite A, right? And so I really want this, right? So there has to be some correction that I don't know what it is, right? There's some error, there's some difference. This is going to be, in general, some number, right? And if A is sufficiently small, it's going to be some, let me call it some coefficient, C0, right? Some number times A to some power, right? But there's going to be other corrections. There's going to be, in general, a series of connections or corrections. There's going to be a large number of terms that behave like this. Okay. So in general, I have this relationship. What I obtain is this thing, right? It's equal to what I want, right? And there's going to be a bunch of terms that all scale like a to some power, all right? And so the big O notation is telling you which is the biggest term of the series. And the biggest term is dictated by, for small a's, right, is dictated by where does the series start? Meaning, does it start when n equals 0? Does it start when n equals 1? I mean, it has to start with n equals 1 or higher. So does it start with n equals 1? Does it start with a equals 2? N equals 2? Where does it start? Let's assume that it is the case that it starts with n equals 2. Right? And it goes to infinity, right? Let's say. So then this thing is equal to L of 0 plus C2 A0 2 plus C3 A0 to the third, right? But because A is less than 1, A squared is greater than A cubed, which is greater than all the other powers. Okay. And so this is bigger than this, right? And so this whole thing, all this nasty series in the big O notation is just denoted as big O A0 to the second power. It's telling you there's some series of terms. I don't know what it is, right? But I know that the biggest term scales like this with respect to A. And so that when A goes to 0, if this is the case, then it has to be a quadratic function. And 1 is going to be some value away. Or, well, I mean, it could be something like this, right? Like, right? And then 1, let's say, is far away. And so it's telling you that this is a quadratic, right? A linear term, would be instead something like this. And so why do you want it to be quadratic? Because then if you make a somewhat bigger number, then you know that the difference is going to be smaller, right? Because there has to be a little bit of curvature there. Okay. Does that explain the big O notation sufficiently well? Let's hope so.
I believe so. I think we've covered everything. I'll let you know if anything changes. There's no current questions, I believe. But...
All right, cool.
Oh,
all right.
The original asker says they're still confused on what the big O actually represents numerically. But I think what they're confused about is that it's a function of A, not an actual number.
Yeah, O is a function of A. It's not a number. This whole thing, big O, just means there's a series of terms with the largest one having this power. It's a confusing concept and it's not immediately necessary. So if you're struggling with it, perhaps put it aside for a little bit. It's not going to be immediately relevant for what you're doing. It's going to come up in whenever you're dealing with anything that is numerical in nature. We use it a lot in particle physics. it's used a lot in quantum mechanics. So you'll encounter again if you're considering any of those fields. But it takes a little bit of time to sink in.
We also have an additional question asking, in the first series, why did we sum a constant times a to the nth power?
Well, I'm just saying if a is okay. I'm assuming the a is sufficiently small, so I'm doing a Taylor series around a being 0. So this is justified by calculus. That's the easiest way that I can justify it. So I'm assuming that a is small, so I'm doing a Taylor series around a being 0. The first term is 0, and then all the other ones are coefficient. I mean, they're just followed by corresponding derivatives of this function multiplied times a to some power.
Ryan would like to follow up with that. They're asking, doesn't the Taylor series use factorials?
Yeah, I mean, that's all hidden in this thing.
Yeah.
This is just a number. I don't know what it is.
Be anything you want.
Yeah, it's just to be some derivative with the appropriate coefficients. Yeah.
I think that covered the second original question that we had. So.
Sounds good. All right, maybe let's move on. If this is the thing that is holding you up, like I said, it's not immediately relevant. You're gonna see this again, so don't lose sleep over it just yet. Okay. Okay. So then, going back to our task at hand, we've rewritten. So we did a little bit of trickery to rewrite the second order differential equation in terms of 2 first order differential equations, which would then translate into algebraic equations. So that's easy. And so that's very clever. That's very nice. And then once we have that, we can then solve them iteratively, just like the way that we solved the first order differential equation. I put a whole lot of comments, right, explaining all this. And this is all in my code, which is in the Dropbox. Oh, wait, newbie. Haha, forgot about this. And I'm saying newbie out of kindness, I'm not picking on you. So if you're new to this class, at Python for Physics at odu.edu, and then you'll get a whole lot of links to stuff, including links to our Dropbox, where you'll see, as well as the recordings, which will just take you to a YouTube page. And then in our Dropbox, I have all my slides, notes, and codes. So you have access to everything. The power is yours. All right, back to the code. Okay, so in the code, you will see a whole lot of comments. You have all these comments. You have even typos, because I don't know how to spell sometimes. And remember, to solve this, I need to know h, right, which is a function, and you can input functions into functions. I need to know the first value of f, which I'm calling f naught, the first value of g, which I'm calling g naught, and then the times over which I'm evaluating this, which is the independent variable, and then the spacing between the points. All right, and so then what do I do? Well, I just create lists for my output, both for the function and then the derivative. And then I just loop over the times. I do my step for g's, okay? I do my step for f's. I append into my list. I append to the second list, and then I return the list. Easy. There's some subtleties about the time, right, for g's, but I explained that here, and I take the average between the 2 points. You don't have to do that. Just improve things a little bit. Okay. All right. So hopefully that's clear. This takes, there's a lot of comments there for you to read, but hopefully, they help and not hinder. All right. So now let's put your code to a test. And again, this is there to help you, but you should try to write your own code. Try to do it on your own first. Just try to map the equations into some pen and paper, figure out, think about the logic real hard, and then start write some pseudocode, right? And then start writing the code yourself. Anyways, let's put some examples. So here's some examples, some exercises. First one, let's do the simplest case. This code should work for any acceleration, right? Doesn't have to be constant, doesn't have to be anything. It should work for any acceleration. But that being said, let's set the acceleration to 0. Let's set the original position to be at 0 and the initial velocity to be 1. Okay. What's going to happen? Well, the acceleration is 0, so the velocity should not change, right? And so this is what I'm getting. The numerical solution is the red for velocity, right? Here's my input for acceleration. I have the original point velocity. It doesn't change. It stays at 1, 1, 1, 1, 1, 1, 1, right? The acceleration, the position, right? It should have a slope of 1. And indeed it does. And I get this red, beautiful line. And then the green are the expected values, right? Expected values, I'm just using the equation that Ted gave us. Cool. Simple enough. This should make you feel like you're on the right track, but it's of course not enough. Now let's look at a case where now you have acceleration, and I picked acceleration to be negative 9.8. Why? Because it's the constant acceleration of gravity approximately on the surface of the Earth, right? So I picked negative 9.8. And then I gave my original particle to be at 0, meaning it's 0 position and having no velocity. But now the acceleration is negative, right? And it's constant. So that means that the velocity has to be constantly decreasing, or the magnitude is increasing, but it has a negative value. So it's constantly decreasing with a slope of negative 9.8. And indeed it does. The red is my numerical solution. The green is my expected solution. And then last but not least, here's my position. And I put in my expected solution with thanks to Ted, where the original velocity is 0 and then the original position is 0. So then all I have is the acceleration, which is negative 9.8 divided by 2 t squared. And you see I have a quadratic behavior, and that's exactly reproduced by my numerical solution. Beautiful. All right, last example. Last one I have for you is, I told you, so the last two examples at least convince you, hopefully, that these equations that Ted gave you are indeed the solutions to second-order differential equations, assuming the accelerations are constant. Great. So that's awesome, but this should fail if the acceleration is not constant, right? Or at least there's no reason why it should work, right? Well, let's test it. So here's my acceleration, where now I'm not going to set it to be constant. Now I'm going to set it to be linear in time. And the coefficient, I'm going to set it equal to 1. Good enough. And so here's my acceleration. It's increasing as a function of time, right? And in red is my numerical solution, all right? And in green, for the velocity, and time is on the x-axis, in green is what I would get if I assumed that the acceleration is constant, but it is not, right? And so I get a different solution. Aha, okay, we see that this is not working. And finally, for the position, you see the position, I get this red, right, solution. And in green is what I would get if I just assumed that the acceleration was not changing. I'm off. Good. All right. So these are simple exercises. They hopefully build some confidence, some intuition, right? But they're more useful. They're going to be useful for many sets of differential equations. And in fact, next time, Ted is going to show you how to use the same kind of technology for solving differential equations for infectious disease models. Their life is going to be slightly more complicated, but not that much more complicated. So I'm going to encourage you to stay tuned to check that out. That's going to be a really cool example. And the science behind it is just really neat. I mean, those models are pretty cool. So please stay tuned for that. Let me just do a little recap before I take some questions on the concepts that we learned, right? We reviewed concepts of position, velocity, and acceleration in physics. We introduced calculus and differential equations, both first and second order. We were able to find, rewrite these in ways that are simple for us to code up. And so we found solutions that are algebraic in nature that we can just iterate numerically. And maybe the most interesting concept that we introduced for Python is that we were, for the first time, writing equations which its independent variables are also equations. That's very powerful and is something that you may want to use later on in your career. So, okay, so I think that's all I got. Are there any questions before we call it a day? Everything was super clear. I mean, I like it when it's clear.
There is a question about the Dropbox, whether the second differential equations code is in there yet.
Good question. I thought it was. Mm-hmm. What's that?
This is a funny comment that Anonymous says that the only thing keeping them sane right now is coffee because calculus is so mind-boggling.
Yeah, the code is there. So I have a piece of code called Finite Diff in project #5. If you search around line 462, solving second order differential equations.
They say thank you. So
Go.
And then one final question, it seems, asking, until when will the mentorship program continue?
Yeah, so I mentioned this before, but the idea is that we're gonna start it. We're gonna lecture probably for a few weeks, and we're gonna create projects that people are gonna have to reproduce. After that, I would say that's gonna be maybe 5-6 weeks in total. After that, it's up to you if you want to continue. And we're gonna, as I said, it's gonna be hard for us to continue working with everybody. But what we'll do is either try to find other mentors across the world that maybe match your interests, or we may continue working with some. So, but at least you're gonna have the opportunity to work on some projects that are a little more advanced that are, some are going to be numerical in nature, some are going to be analytical in nature, but they're going to be more advanced than what we would teach in this course. And if you're a little behind in Python for STEM and you're in my mentor group, then my task is going to be mostly for you to catch up, and that's okay. So what I want to do is try to engage you, make sure that you're building these tools, which we think to be useful for lots of different fields in science. And so We just want you to take the time to go through it. And if you're moving forward ahead, then don't worry. We have plenty of challenging, interesting projects. So, all right. Anything else? This is our last moment together. Cherish it. I mean, I'll see some of you often enough, but in this format. All right. Well, if there's nothing else, it's been a pleasure. Yeah, it's just been, I love teaching this class with you guys, and it's, you guys have been fun. I hope you've enjoyed it. I wish we could do this in person. Everything is so much more fun in person. But some of you are kind of far away, so we wouldn't have been able to be in person if it wasn't for this format. So thank you so much for taking your time and engaging with us and learning about this concepts. Don't forget, you're welcome to participate in the REYES trivia night. That's going to be with Andrew Dodson, who is just a whole lot of fun. So this is only fun if you nerd out with us. And for you to be able to nerd out, you have to go check out the videos and learn as much stuff as possible. And also, I would encourage you to try out this idea of making little videos of your own, describing concepts that you're learning. We've heard from many people that this is an excellent way for you to digest information that you're learning, right? I don't learn as well. I don't learn a concept as deeply as when I have to teach it to others. And so if you think that you understand something and then you make a video where you have to explain it to somebody else, it's going to force you to understand it even better, right? And you can have to do your research and think creatively. And that's just a skill that is just going to be useful for any career path you decide to pursue. So I strongly encourage you to participate in that. It's going to be a fun opportunity. And yeah, I agree with Anonymous. Thanks to Greg for all his hard work, but he's not off the hook yet. So he still has work to do. And so you'll be seeing more of him. And yeah, thanks everybody. Thanks, Philip, Adriana. I'll see you guys. I mean, you're going to be in my mentor program, right? So I'll see you then. And yeah, I hope everybody's having a good day, and we'll see each other later. Okay. Oh, and don't forget, we are going to have more. We have some surprises coming in REYES, and there's going to be some lectures coming up in the fall and the spring. And there's a secret surprise that I'm still working on. So stay tuned, stay connected. We'll have more stuff for you coming. Cool. All right.